Konnichiwa. How is everyone doing today? It's nice to see all of you here at this session. I want to start by sharing that it's a great honor to be speaking in front of so many fellow developers here in Tokyo. I am Jihong Lee, and I'm part of the data science dev team at Line, and our team works on providing our users with machine learning solutions. Today, I'm going to give a talk about the Line timeline post recommender system. Some of the topics that I'm going to go over today may be trivial for those of you that already have a background in machine learning, but I've prepared the speech thinking that part of the audience won't be familiar with these concepts. So please bear with me through some parts if you are already a skilled machine learning engineer. I will start with what a recommender system is. Then I will explain how we implemented them in our context and go through some problems that we encountered with our solutions to them. I will add on to the solutions with some lessons that we learned in the process. So before we get started, can I get a quick show of hands of who knows what a recommender system is? That's okay. We can get to know them now. Whether we realize it or not, recommender systems can be found easily in the world we live in today. They have situated themselves seamlessly in our lives. Let's take a look at some examples. When you go on Netflix, it gives you a list of movies or TV shows that you may like and watch. Instagram recommends you photos or videos that you may enjoy and consume time watching. Spotify gives you radio stations or lists of songs that you may want to listen to. And Pinterest recommends you pins and boards of content that they think you would like. Now you get the idea. And of course, we at Line also serve recommender systems to our users. My team in particular serves our users with recommender systems in Line's timeline tab. So in case there's people that don't know what Line timeline is, I want to introduce it for a minute. Line Timeline is a social networking platform within Line Messenger where users can upload posts and videos to share with their friends or subscribers. We call this screen the timeline feed. You can get redirected to a page for only official accounts that you have subscribed to. This page, at certain selected positions, we recommend users with posts that they may like. For those of you that aren't too familiar with what a recommender system is, I'm going to take a minute to address some background knowledge before I go into an explanation of how we implemented ours. There are two big approaches when it comes to building recommender systems, which are collaborative filtering and content-based filtering. Let's take a look at the first one. Let's suppose we have a matrix that looks like this. Here, the row fields are users and the column fields are movies. The values inside each cell can be thought of as ratings that a user has given the movie after watching it, with 1 being the minimum and 5 being the maximum possible values. If we look at the green and orange users, we can notice that they have watched 2 movies in common, movie A and movie B, and they both gave good ratings for them. Using this information, we can infer that the green and orange users have similar tastes in movies. Also, notice that the green user has watched and enjoyed movie C, which the orange user hasn't watched. Since we have already made the assumption that the green and orange users have similar tastes, we can predict that the orange user will also enjoy movie C. Therefore, we can conclude that giving movie C as a recommendation to the orange user should be considered a good one. Nice, right? One thing we can take away from this method is that we are able to make valid recommendations without having to know anything about the users or the movies. The only information we are using is the ratings that the users have given the movies. This can be thought of as a very simple example of a recommender system. Now, let's move on to ours. Before we start implementing models, we need to define our problem. What we wanted to achieve was to train a model that is given a user and a post with context and outputs the probability that the user will click the post. Let's look at the procedure followed when servicing a recommender system. First, we start out by collecting raw data. Then, we pre-process the data. Next, we choose an algorithm and train the model, which is then deployed to recommend content to our users. This finally causes user interactions that can be used as raw data into our next model. To be able to train a recommender system, we first need to change our raw data's format into one that a machine learning algorithm can interpret. More specifically, to perform a supervised task, we need labels that represent the ground truth. In the previous collaborative filtering example, we had ratings that users gave movies on a scale of 1 to 5. This kind of data is called explicit feedback from the users. We at Line lack a system where users can give ratings to posts. Therefore, we must infer them through actions like likes or clicks that the users have made. This kind of data that we created our training set on is called implicit feedback. So, how did we do this? Let's take a look at what our raw data looks like. First, we have a user view history log. Simply put, this log is a collection of data on which users viewed which posts at what times. We call these views impressions. We also have a user click history log, which is similar to the view log, except that it has information on which users clicked which posts. Using these two logs, we can create labels of user post interactions. How? We just joined them, right? Joining the logs gives us this format, which is the labeled data format we desire. Positive labels occur when a user viewed a post and made a click for it, and negative labels occur when a user only viewed a post without making a click. Using this data, we can train a supervised machine learning model. So now let's move on to the next step on the pipeline. Now that we have our data and trainable features, isn't the rest pretty straightforward? We just choose an algorithm, train our model, evaluate it, then deploy the model to service to our users, which causes user interactions. This is simple. End of presentation, right? Unfortunately, when something seems too good to be true, that's usually the case. And here it is too. Life isn't that easy. There are various problems that we encountered when trying to train a high-performance recommender system, and I will address these next. They occurred in the pre-processing and model training steps of our pipeline. Let me start with some recommender systems 101 before introducing the problems. When starting machine learning tasks, we need to pre-process our data. We usually start with a feature matrix, where features are just attribute values that can be anything as simple as someone's age or gender. We could theoretically use this feature matrix directly as input to train models, but there are some issues with this practice. First, the dimensionality, or the number of columns of the data, is too big. A feature matrix of high dimensionality will require very expensive computational resources. And second, there's no meaning in the categories. In other words, the representation of the features in this space doesn't give us much insight on the distribution of the data. Therefore, it is a common practice to transform this matrix into what is called an embedding representation. When we train embeddings, what we are trying to do is, first, reduce the dimensionality of the data, and second, find important factors and connections within the data that are not visible in the original dataset or to the naked eye. By doing this, each column or combination of columns will have a certain meaning. In other words, embeddings capture some of the hidden meanings of the input by placing semantically similar inputs close together in the embedding space. Now, since everyone has an idea of what embeddings are, let's get into our first problem. Creating embeddings is a crucial part in machine learning. Properly made embeddings make it easier to carry out and increase performance of machine learning tasks on large inputs. We had a problem when trying to train them, though. We started out with a matrix of user post interactions. What we want to do is predict the values for the empty cells by creating a space where similar users and posts are close to each other. A common way to achieve this is to factorize or divide the matrix into two smaller matrices with smaller rank, one with user embeddings and the other with post embeddings that attempt to replicate the original when multiplied. The common thing about approaches like matrix factorization, the factorization machine, and Bayesian personalized ranking, for example, is that they all directly model user embeddings. These approaches are known to work, so we assumed that they would work on our timeline data too. However, we were thinking about the problem too naively. The user dimensionality of line timeline is extremely large since we have close to 100 million users. This number is also constantly growing by the minute. The user post matrix is extremely sparse, with the density being approximately 0.0001%. This means 99.9999% of the cells in the matrix are empty. Therefore, the number of interactions per user compared to the number of posts is too small to be able to define user preferences just based on their interaction histories. So we tried implementing many algorithms that attempt to directly model user vectors, but none of them gave us merely desirable results. The user vectors that were made did not seem to supply us with much valuable information about the users, so we needed to find another way. This was the first problem that we faced. So we moved away from the user post matrix that attempts to directly model user and post embeddings and pivoted to using a post-to-post co-occurrence matrix and first modeling post embeddings. Then we computed each user embedding as a linear combination of the embeddings of the posts the user has interacted with. By doing this, we are putting the user and post embeddings in the same vector space. Using these user and post embeddings as features gave us much better results than trying to model user embeddings directly. They showed meaningful improvements in offline and online evaluations. So, what lessons can we take away from this? When we are new to building recommender systems and we form a user item matrix using our data, it is tempting to look up and use an existing matrix factorization library or sample code for algorithms to create our user and item embeddings. However, the algorithm of choice must depend on the sparsity of the data. Just because an algorithm worked well on the Netflix or MovieLens datasets doesn't necessarily mean that you will get the same results using your own dataset. So the lesson that we learned is, before we choose an algorithm to fit on, we must look into the nature of our data, since different algorithms are suitable for different types of data. The second problem I will address is an issue with training data bias. If we train models with biased training data, we will fail to correctly capture the distribution of the user's interactions with posts. Let's look at what this means. Looking at our training pipeline, our model is trained at a certain point in time and deployed to service our users, which causes user interactions. These interactions are then used as raw data when training our next iteration's model. This may seem straightforward at first. However, the fact that the user interactions caused by the model are used as input data for the next model is problematic. So how could this be a problem? Let's take a look. Suppose there is a model trained at time 0, and let's call this model model 0. This model is used to give recommendations to a user. Then the user interacts with these recommendations. Here, we have to note that these interactions were directly caused by model 0, and that there is a good possibility that the user will not have been exposed to these posts otherwise. If the data of these user post interactions are used to train model 1, the distribution that the model trains on does not accurately represent the preferences of the user. If this process is repeated over time, the models being trained will be heavily biased towards the posts that were highly ranked by their predecessors and will not capture unbiased user behavior. This is called a feedback loop, also known as previous model bias. So, how did we alleviate this issue? When our model is trained and deployed, it gives recommendations to users when it receives queries. Interactions between the users and the recommendations occur, but when collecting raw data for the next model, we excluded all the interactions that was a result of our models recommending. We also excluded all the interactions that were made from the posts written by authors the users have already subscribed to. This leaves us only with interactions made from users' engagements with posts that their friends have shared or the authors they have subscribed to have shared. In essence, we only trained the next models with random interactions that could not have been anticipated by the user or our model. By doing this, we have eliminated the feedback loop. The next problem I'm going to go over is one about evaluation. Evaluation is a key part when training machine learning models for a certain task. I'm going to talk about our offline evaluation method and what problems arose with it. We use AUROC as our offline evaluation metric, which is the most widely used evaluation metric for classification problems. It is a curve of the true positive rate plotted against the false positive rate, and it is a ranking measurement of classification performance at various threshold settings. The dotted line that goes through the plot diagonally represents the ROC curve of a random classifier, which just means it's a coin flipping 50-50 model. We want to train a classifier like the solid line, whose area under the curve is much larger than that of the dotted line. The blue area here is the value of the AUROC metric for the trained classifier. Before we test models with actual users, we compare their performances offline by their AUC scores. We choose the models with scores higher than our existing model in service and put them into A/B testing with the expectation that the new developed models will outperform the existing in KPI. However, in many cases, the outcome differed from our expectations. We took a deeper look into what was going on and found out that there was a fundamental problem with our offline evaluation method. We had been calculating AUC at once for the whole testing data set, but we realized that training a model that would have a high AUC score for the whole testing data set can actually be translated into training a model that ranks at the top posts that would be liked globally throughout all users. In other words, we were putting all the users into one giant user and then ranking the posts. So, how is this a problem? Our goal is to provide each user with personalized content based on their preferences, but this aggregation of users was going against our fundamental goal. The best classifiers based on our evaluation method were those that ranked at the top posts that they thought would be liked by the most users, not by each user individually. Therefore, we realized that we needed a change in our offline evaluation method. So, instead of calculating the AUC for the whole test set at once, we changed to calculating AUC for each user separately and then averaging them. This way, we would be getting individual scores for each user's personalized recommendations. This may seem like a very minor detail, but it was actually a factor that made a very big difference in our service. Many research papers say that they use AUROC as their evaluation metric, but don't go into the details of their evaluation method. So the lesson we learned is that choosing a metric only gets us halfway, and that we must formulate a method that achieves our goal. Next, I'm going to talk about changes we made to our model's architecture after some realizations from data analysis. It's going to take a second to get a sip of water. We were trying to pull off the whole system with just a ranking model. And there were two major problems with our model's pipeline. So what were the problems? When thinking about our problem description naively, we can think that if we have a model that can give a ranking of posts for each user, we can just shoot all the posts we have in as input whenever we receive a user query and give recommendations accordingly. But given the size of our post corpus, doing this meant that we had to invest substantially in service equipment. So we did. Just kidding. We developers don't have the luxury of assuming that we will have an unlimited supply of resources, so we needed to find a way that would work. And this was the first problem. Another problem that arose with using only a ranking model was that given the extremely low density nature of our data, and that a high proportion of the interactions were concentrated on a small subset of posts, when we put all the posts into a ranking model, which was trained to predict click probability, the model returned a similar list of posts for all users. And since we wanted to supply personalized recommendations, this was a critical problem. So after doing some research in search of solutions to these two problems, we decided that we could implement a method where whenever we receive a user query, we select a small subset of posts from the corpus that matches the user's preferences, and we call these candidates. And then we would give these candidates as input to the ranking model. This would decrease our need of computational resources significantly and be able to provide personalized recommendations. This is when the division of our model into candidate generation and ranking happened. Before I explain our revised model architecture, I want to address a concept called Pareto Optimality. It is an economic term that can well explain our situation. Any economy has preference criteria, or factors that it considers important. Pareto optimality is a state of the allocation of resources where it is impossible to reallocate so as to make any one preference criterion better off without making at least one preference criterion worse off. This green line on the graph is called the Pareto Frontier, and any allocation of resources on the Pareto Frontier is Pareto optimal and is where we want to be. In our context, the preference criteria are personalization and KPI, which is short for key performance indicators. Our goal was to maximize personalization and KPI. However, by using a sole ranking model with our data, we did not seem to be providing much personalization. We thought that only by providing some level of personalization could we also maximize KPI, and that there had to be a point in the space we were traversing where this allocation of resources existed. Our hypothesis was that by using only a ranking model, whenever our model was trained, it was converging at a local maximum of our preference criteria. We wanted to get to the Pareto frontier. More specifically, we were still shooting for an allocation of resources where both our preference criteria were somewhat met. However, we didn't want to maximize KPI without any personalization or maximize personalization with very low KPI. So we were actually shooting for a point on the frontier along the lines of the 3 points on the graph. And we thought we could do this only by changing our model's architecture. So we decided to train two separate models, a candidate generation model that trains co-occurrence-based post embeddings, and a ranking model that trains on predicting click probability. Recall that we modeled user embeddings using linear combinations of the post embeddings that they have interacted with. This way, the user embeddings and the post embeddings are in the same vector space. What does this mean? Now, when we receive a user query, we can calculate its user embedding, which can also be thought of as a vector representation of the user's interests. Then, we can select a small subset of posts from the whole post corpus by finding close post embeddings to the user vector using methods like local sensitivity hashing or FLAN, which are both well-known methods. The speed of doing this is much faster than putting the whole post corpus into the ranking model. And the candidate generation phase here has two components. The first component is the training phase. In this phase, we start with the post co-occurrence matrix or a post sequence matrix. With this data, we transform them into post embeddings, like we saw earlier. The inference phase is a little more complicated. This is when we are actually giving recommendations to specific users. First, we receive a user ID. Then, we see what posts this user has interacted with. Note that we have trained embeddings for these posts in the candidate generation training phase. Then, we perform a linear combination of the post embeddings in the user's interaction history. This gives us the user vector, or the user embedding. Since the user embedding and post embeddings are in the same vector space, we can just perform a nearest neighbor search to find posts that are in the user's taste. This gives us the candidates for the user, and these candidates are going to be used as input to the ranking model. The inference pipeline in a simpler form looks like this. We receive a query for a user, the candidates are generated for the user, Then the candidates are then ranked by our ranking model, and then the user receives recommendations based on their ranks. Now, this seems like a pipeline that would work, right? And the last issue I'm going to address is one that is common to any social networking platform. The number of users, posts, connections, and the size of aggregated content continues to grow. The problem is, we do not have the luxury of constantly stacking computational resources for training and inference. In our case, the biggest problem was the increasing size of the post pool. We perform the training of our candidate generator in scheduled batches. What this means is that we are training new models using the data for each time step. Let's assume, just for simplicity, that we train a new model once every day using data in the recent week. Let's call the first model Model 0, the second model Model 1, and the third model Model 2. Then, Model 1 will have trained on the data for days 1 through 7. Model 1 will have trained on days 2 to 8, and Model 2 will have trained on days 3 to 9. So we can see how they will have different post pools. However, what we want is to have all the posts in days 1 through 9 in our post pool. It would be nice to be able to train with an increasing amount of data at every model iteration, but unfortunately, our resources are limited. So, how could we do this? This meant that we needed to implement a method that would be able to align embeddings trained at different points in time without having to constantly increase the amount of computation done during the candidate generation training phase. And this brings us to the orthogonal Procrustes problem. The problem is defined like this. Given matrices A and B, which have the same size, we are trying to find an orthogonal matrix W such that the squared Frobenius norm of BW minus A is minimized. We are attempting to find the rotation and reflection, or just the optimal orthogonal linear transformation that will transform matrix A as closely as possible into matrix B. Let's try to visualize this. We can plot the vectors in matrices A and B on coordinate planes, since vectors can just be thought of as points in a vector space. And here, we are assuming A and B are two-dimensional matrices for simplicity. Can you see the resemblance between the shapes and the plots? If not, let's put them onto the same plane. Now we can see the resemblance a bit more clearly, right? One prerequisite of the orthogonal Procrustes problem is that there must be a one-to-one correspondence of points between the points in matrices A and B. That is, A and B have to be comprised of pairs of directly related points. Using these matrices, we are trying to find a rotation and reflection that will transform and hopefully turn B here into A. And once we have trained for the transformation matrix W, we multiply B to it, and we get an aligned A and B. Although they are not perfectly aligned due to the difference in distributions of the data they were made from, the alignment seems to have worked pretty well. This was an example of the orthogonal Procrustes problem. But the important thing now is, how did we use this method to solve our problem of increasing post pool size? We have post embeddings trained at different points in time. Although they have different post pools, since we train on a long period of time, a vast majority of the posts that consecutive models train on overlaps. Let's call the overlapping embeddings in time 0A and those in time 1B. And of course, they have the same shape. Due to the nature of the algorithm that we train the embeddings on and the changing distribution of the training data across model iterations, the same post will have a different vector in times 0 and 1. And when I say different here, I mean different in direction and magnitude. However, if we make one important assumption, we can apply the orthogonal Procrustes problem to our data. The assumption is that the angles between the embeddings in matrix A and the angles between the embeddings in matrix B are similar. Once we make this assumption, all we have to do is find an orthogonal transformation matrix W that can rotate and reflect matrix B into matrix A. So now that we have found the orthogonal transformation matrix, we don't just transform the overlapping post embeddings in time 1 into the time 0 space, but we apply the transformation to the whole time 1 embedding matrix. This means we have transformed the time 1 embeddings into the space of the time 0 embeddings. Let's call the transformed matrix time 1 prime. We can see that the embeddings for posts 3 to 7 have been aligned. They're literally the same numbers. Now, if we take the posts that only exist in time 1 prime and concatenate them to the time 0 post embeddings, we have aligned the embeddings trained at different points in time. By doing this, we proposed a solution to solving the problem of an ever-growing post pool using limited training resources. We experimented with this method and tested it by calculating the average cosine similarity between the post embeddings that overlap and got very good results. This is significant because the aligning of the post pool does not have to be done during the candidate generator training process, hence the lower pressure on computational resources. To wrap up this presentation, I want to go over the topics that we went through today. Before jumping into modeling, you need to understand the nature of your data you are working with. Only when this is done can you figure out what kind of algorithm to look for and implement. When evaluating the models you have implemented, don't get too excited just because your model shows good performance based on your evaluation metric. There may still be factors of your model that don't meet your end goal, so always perform qualitative analysis also to check if your model is behaving in the way you desire. Also, there is a strong need to understand how your evaluation metric should be used to meet your model's goal, since your evaluation method may not be suitable for your objective. Even if you have a great algorithm, if the architecture of your model is not optimal, you may have trouble getting to the performance point that you want to get to. And constantly tuning an algorithm over and over again may not be the way that you achieve your goal. So always keep in mind changes that you can make to your model's architecture in order to increase overall performance. Lastly, I want to share a quote that I always have in the back of my head. Perfection is not attainable, but if we chase perfection, we can catch excellence. Thank you all so much for taking the time to come and listen to this presentation. And please feel free to come by to the Ask the Speaker session with any questions regarding this presentation, and I'll make sure to get back to you with my answers. どうもありがとうございました。